Okay, so I'm going to put up where we were at the end last time. I was discussing what it would mean for a closed quantum system to thermalize, to go to thermal equilibrium. So we have the probability operator for the subsystem. Let me remind you. So we have our system, close to the box. And we have our subsystem. And I call the rest the bath. And we're going to take this to infinity. So n goes to infinity corresponds to taking the system large. Time to infinity. Time to infinity. We have a Hamiltonian of this full system, which has possibly some conserved densities. And the equilibrium state, the final equilibrium state, depends on if there's a conserved energy, it corresponds to a certain temperature. If there's a conserved number density, it corresponds to a certain chemical potential, etc. So we have one parameter for each conserved density. And then the equilibrium probability operator for the subsystem is given by the trace of an equilibrium distribution for the full system in the limit n goes to infinity. Now, last time I said, let's take this as Boltzmann gives, but actually here just use any convenient ensemble. Okay. So we could use the microcanonical ensemble here, we could use the canonical or some mixed thing, grand canonical. And the point about thermalization of infinite systems is the properties are the same in all the ensembles. That's what you learn in statistical mechanics. You get the same results whether you do whichever ensemble you do. Right? So this is just a case of that. Just going through it carefully in terms of quantum mechanics. Okay. And then I just wanted to say one more thing, which is there is this interesting case, which is the Floquet case, where there's no conserved densities. Right? So if you have a kicked system, energy conservation is gone. And if you have no other conserved densities, there's no conserved densities. And so then what it goes to is infinite temperature. It goes to the maximum entropy, no constraints, and so it goes to what? The identity operator. So this goes to the identity operator. We have to normalize it with some partition function, and this would be for a Floquet with no conserved densities. Yeah.
And rho S equilibrium has to be a canonical distribution, right?
Yeah, this is right, and it's the usual story, right? This is in contact with this bath, and so it is the ensemble you get for a system in contact with the bath, exchanging whatever it's exchanging with the bath, right? And so actually, if there's a chemical potential here, you call it grand canonical, right? If it's only a temperature, you call it canonical. And an interesting point about the Floquet example is, you might ask, the system thermalizes if it can be a bath or a reservoir to equilibrate its subsystems. But what does it mean to be a reservoir, right? And usually you think, oh, you're exchanging one of these conserved densities, right? That's the usual thing, right? Exchange energy, exchange particles. But here it's not exchanging any conserved quantity, right? But yet we still have the same structure, really. It's just somehow less interesting. There's no parameter. But what the thermalization really is, it sort of points out what the essence of the thermalization is. It's not really exchanging these conserved densities. What it is the information about, all information about the initial state is being spread over the whole system. And all information about the initial state is everywhere in the whole system. In this case, there's no conserved densities. And so all initial states in the thermodynamic limit go to the same thing, at least as far as looking at it locally, which is just this maximum entropy state. But if you have a conserved density, the conserved density is uniformly spread over the whole system, but the subsystem gets its share, and the parameter t tells you what share of the energy it gets, and this tells you what share of the particle number it gets. But it's saying the essence of the reservoir is really transport of information. And a reservoir, the key thing it does when it thermalizes something is it exchanges quantum information. It really takes the quantum information and decoheres the system. And that's really the essence of it. It isn't essential that you exchange energy or exchange particles. And the Floquet example is nice because it illustrates that. Yeah.
So is there a way that I can write rho subsystem equilibrium as usual canonical density matrix, canonical density operator, like e to the minus e over...
With this guy?
No. That guy.
This guy?
Yeah. Is there a way I can write it as e to the minus beta times h sub s?
Well, you could take the logarithm of this and call it h sub s.
Yeah, so I can call that.
Yeah. And for a large system, it will be, to a good approximation, the Hamiltonian of the subsystem, but it'll have added terms from the surface terms. But I want a construction where this can be a very small system, which is very strongly interacting with the bath. And so most of its Hamiltonian is not within the subsystem, its interaction with the bath, and it's been removed here, right? And so that's why I'm avoiding saying that this is the exponential or the Hamiltonian of the subsystem, because that's really not the case in general. There's specific, if you have a system and it's very weakly coupled to the bath, that is the situation, but that's not the case generally.
What if on this equality, we place the limit t goes to infinity by averaging over time, by the integral from 0 to big T over little t?
No, you can do that, as long as you average all the way out to infinity, because the initial transients will carry no weight in the limit. But I think it's a stronger statement, right? See, that's a weaker statement. This is a stronger statement. Namely, it at each time goes to that.
But so that means there would be a system maybe which in the weak sense will thermalize, but in this sense they will not thermalize.
Right. Yeah. But I think, for the construction I'm talking about of a system, and this n goes to infinity, you don't need to do that. It'll go to equilibrium without the time average. For reasons that I'll sort of maybe argue for, I shall say, in a little bit. Yeah?
Does the entropy of the subsystem increase with time?
Depends on your initial condition. Or if the subsystem is initially hotter than the rest of the system, the entropy will go down.
Okay.
Yeah. So that's...
But does it do so uniformly, or?
You could probably come up with examples where it was non-uniform, right? Somehow, there were two time scales of the exchange, and one of them went one way and one went the other way, right? Say you have energy exchange and particle exchange, and one's much faster than the other. And one of them first lowers the entropy, and then the other one raises the entropy. We've seen, Juan and I have seen stuff like that in the combination of energy and spin transport and spin-Seebeck effect, where stuff like that was happening. So I'm sure you could make examples where that happens. There's no monotonicity claim, no Boltzmann's H theorem or anything like that. Okay, so right, it's a strong claim, right? And so the suggestion is, right, we don't have to time average. It's true for all initial states, and it's true for all subsystems, modulo the criteria that I mentioned last time. So that's the claim. That systems, when systems go to equilibrium, they go to equilibrium in this rather strong sense. Right?
Oh, but also I have another question. So rho is an operator, or you can think of it as probability distribution. If rho is diagonal, for example. But is it possible that maybe there will be some rare states on which rho on the left, t goes to infinity rho, and the rho you find on the right will give you different answers, but that will not be important if you try to average anything over these rho in the n goes to infinity limit?
Well, that's the question. Do you have exceptions? Do you have initial states which are different?
Well,
right.
That's not what I mean. So I mean, how should I put it? So there will be, so rho acts on different states, and when, let you think of rho as probability distribution.
Right.
Rho is that.
But this is a function of the initial condition, right? And so we could get you're asking, could this be true for most of these, but there be rare exceptions, right?
Yes.
Right? And the rare, and this is just one quantity, so if there's rare exceptions, it's special cases over here, right? And the special cases are special initial conditions. So you're asking, are there special initial conditions that do not thermalize? Right? And we don't have evidence that they exist, but it's not a proof. And I'll sort of give some, well, I think, in order for that to be true, but I guess you can keep in mind as I go along, if that was true, what other statements I'm going to make would also, if there were exceptions, there would be exceptions to various later statements, right?
Excuse me.
Okay, sorry.
So
Go on.
the quantity on far left is initial condition dependent?
Yeah, because this is
But
right.
What about the quantity on the far right? Is it initial condition dependent?
No, the initial condition is only here, right? There's no time over here, no time over here. This is equilibrium, this is equilibrium. This is a definition, right? And this is equilibrium, right? But this, you have some initial condition, you go to infinite time.
Can you remind us how the one on the left is defined, rho s defined?
Yeah, okay, so rho s of t is trace over b of rho of t, which is rho, let's say n for the, just of 0, e to the minus I ht, e to the I ht. So this is the probability of the full system. Here's the initial condition. Here's the time evolution. Trace over everything else, left with a probability here. So the initial condition comes in here. And so this is a function of the initial condition and the time. But the claim is, for systems that thermalize, although it's a function of the initial condition and the time, it's not a function of the time in the limit of time goes to infinity, and it only depends on just a few things about the initial condition, namely its conserved densities. That's the claim. Yeah.
So if you're testing this thermalization hypothesis, let's put it like that, in a finite system, let's say in a numerical study,
Yeah.
I guess you have to be careful with this limit of t going to infinity, right? Because
No.
in principle,
No, that's easy actually.
wouldn't you have some?
But I'm going to talk about testing this in a little bit.
Okay. But aren't there sort of these Poincare recurrences? If you have a finite.
In a finite system, yeah. But you notice I take n to infinity first.
Right, but that's why I'm asking about the
Yeah.
question in the numerics, right?
Yeah. Well, let me address that when I talk about looking at this numerically. which will happen in a little while. Because I have some specific things to say about testing this. We've done some testing of it, and so I have some experience with that.
David,
Okay.
is this what people refer to also generalized Gibbs ensemble, or?
I'll get to that too. And that'll come probably even sooner than that, than the numerical test. Okay, so if this is true, that this happens in particular for all initial states, as I said last time, there is a special set of initial states, which are the eigenstates of this Hamiltonian, or the eigenstates of this Floquet operator, and they're time independent. So therefore, they must be at equilibrium in this sense, right from the start. And that's the eigenstate thermalization hypothesis, ETH. Eigenstate thermalization hypothesis, no, not theorem. And in fact, it's only true for some systems, and it's false for other systems, and it's true here, it's false here, there's a phase transition between them, and that's what I'm going to be getting to. Okay, so it's just a hypothesis, and it's false for physically reasonable type systems. Okay, so this goes back to some work, Deutsch, 91, really spelled out well by Srednitsky, 94, and that's one of the papers I put on the website. And then I think I also put this Regal paper on, so there's this Regal, Junchko, Olshani. He spells his name differently all the time. 08. What was I going to say? So these people were coming out of quantum chaos, which sort of came from first classical chaos of small numbers degree of freedom, and then quantum chaos of small numbers of degrees of freedom, and they said, what about quantum chaos and high numbers of degrees of freedom? But they weren't really coming out of cold atoms or condensed matter or anything like that, right? And so there was a bit of discussion at this time, and there's some little. And then what happened is these guys sort of rediscovered it and wrote a real nice Nature paper and tested it on some Hubbard models and caught everyone's attention. So this ETH, was something that was brought to a wide community's attention by this nice paper here, and since then there's been a lot of investigation of it by lots of different people, lots of discussion of it. Okay. And the eigenstate thermalization hypothesis is basically we have the eigenstates of the Hamiltonian of the full system, and it basically says we can define we have the probability operator in an eigenstate for a subsystem. So that's trace over the bath of the probability for the full system. So just in an eigenstate, and this is equal to rho s equilibrium at the whatever parameters you here. So this is basically the eigenstate thermalization hypothesis. It's that the eigenstates are thermal, not just the long time states, but the eigenstates also. And those are the eigenstates of the full Hamiltonian. And let me just mention in passing here, I just wrote down here the eigenvalue equation for the eigenstates of the Hamiltonian. Here are the eigenvalues. These eigenvalues when the system thermalizes, these eigenvalues are going to have random matrix statistics. So the lecture you just heard from Alex, these guys have exactly the statistics he was just talking about, right? With whatever symmetry class this system has. Okay.
So you don't need any disorder, I guess you.
No, this is no, you don't need disorder.
So just ergodic system.
Just ergodic system, yeah. It's true for a lot. It's been tested for a lot of non-disordered systems, and if you have a disordered system but you don't have strong enough disorder to localize, it's still true, but then it fails when the system gets localized. And now, if this is true, there's no exceptions to, actually, no, we need one more thing. Okay, so let me just go on. Okay. So all subsystems, right. Now, and that tells you, right, so this here tells you the subsystems has the probability operator of the system at that temperature. If this temperature is non-zero, this is a system with a non-zero entropy density. So we have the eigenstates have volume law entanglement entropy. Right? These eigenstates are pure states. The subsystem is a mixed state. Its entropy is just the entanglement entropy between the subsystem and the bath, and that entanglement is volume law, proportional to the volume of the subsystem, except in the case of zero temperature, where it's less, let's say. Right. Okay. Now I'm gonna. What am I going to do? I'm going to write. Let me write the. I'm going to use this basis. And I'm going to take rho of the full system. Now for the full system, rho is equal to sum over nm. In terms of the basis of the eigenstates of the Hamiltonian, the probability operator can be written this way. Okay, and these guys are just going like rho nm of t is e to the I t in minus m rho of 0. Might have a sign wrong here, but you know how to fix it if I do. Okay, and if the eigenstate thermalization, okay, so first of all, we need, for a system to thermalize, the initial condition here in the thermodynamic limit should have no uncertainty in the density, right? So if there's any uncertainty in the energy, it should be subextensive, right? So the energy density goes to a well-defined value in the thermodynamic limit, and in that case, all the eigenstates which are populated in the initial condition have the same temperature and chemical potential, whatever. And so they all look the same, all the eigenstates that are populated in such an initial condition look the same if you look at a subsystem. And so ETH says if I write this matrix out here, I've got the diagonal, rho 1, 1, all the way to rho, whatever, rho n. And the system is thermal on the diagonal. If ETH is true, and the initial condition is at a definite energy density. So that means if the system, so non-equilibrium, basically, let me say, information about being out of equilibrium is all off the diagonal in this basis. If ETH is true. And going to equilibrium is really just dephasing, that these phases here, with time, they grow. The energy differences don't change. They become very large exponents, e to the I times a very large number, which is effectively a random number. So these things go, for t goes to infinity, these become effectively random. And that's how the system goes to equilibrium. Equilibration is just dephasing in this basis. And another aspect of related thing, I don't know if it's really part of ETH, but part of thermalization is, and then the system has the property that for looking at rho of S, so contributions to rho S of t goes to infinity from the off-diagonal terms add up to something which vanishes relative to the diagonal terms in the long time limit.
Well, why, I think that's an argument why the diagonal, why there's an additional time scale where the diagonal ones first approach the thermal.
No. The diagonal ones, okay, so diagonal ones don't change, right? Because En minus En is 0.
That's the only way.
So these are time independent.
So they already start out
They're already at equilibrium for any initial condition, and they're time independent. So they contribute something to rho S, which is equilibrium. But then you correct it with anything you put off of the diagonal here. And if you want to start your system out of equilibrium, you got to put stuff on the diagonal out, off the diagonal out here in order to change that to something non-equilibrium. And you got to put it together, and all the different terms are adding up with very special phases in order to put the system out of equilibrium. Right? But then with time, they get out of phase, and they cancel instead of adding up coherently. So in fact, being out of equilibrium is being coherent. It means you've got all these off-diagonal terms, and they're adding up constructively in a very special way to get your system out of equilibrium. And then they dephase, and it goes back to equilibrium. It's not that the terms go away. It's just they change from adding up coherently, constructively, to put the system out of equilibrium, to just adding up randomly and contributing essentially 0 in the thermodynamic limit to the properties of the subsystem.
But what's the time scale? Just the gaps? Smallest gaps to control the...
Depends on the system. In a system with conserved densities, it's the it's a Thales time. Slow the diffusion across the system. But yeah, it's a more generally, yeah. If you don't have conserved, so that time, as you make a big system, the Thales energy, the time associated with Thales energy goes up, as the size of the system squared, because it's diffusion. Whereas in the flow case system, where there is no conserved density, I presume it's just a finite time, and if you take the thermodynamic limit, it doesn't do anything. But that's something I've just thought about in the past couple of days, so keep positive about that. Gil?
So another thing is about the statement about the time to equilibrate. I would think that if I look at smaller subsystems, I would see apparent equilibration faster.
No.
But maybe not with the. So I was guessing that I would see the diagonal density matrix, but maybe not with the final T mu.
No.
No?
So let's put my subsystem off in this corner. And let's start off with a temperature gradient across here. This guy's going to be hot until...
Yeah, but it will still have a density matrix and a probability operator that's diagonal. But maybe we can both one distribution.
No. This isn't diagonal. What do you mean? Well, of course we can diagonalize this. Oh, what do you mean is diagonal? What do you mean?
So it looks like some equilibrium distribution, but with the wrong
at the wrong temperature.
At the wrong temperature.
Yeah. So it hasn't equilibrated. It hasn't.
Yeah. But okay.
It's got locally
right. Two times. Like
right. So you could have local equilibrium.
Right. Yeah.
Right.
Yeah.
That's right. You could go to local equilibrium much faster, and then there's a time scale associated with global equilibrium.
Right. So then
but the real time to infinity, it's only going to stabilize when you have global equilibrium.
Yeah, but in terms of in the reduced probability operator or reduced density matrix, when do the off-diagonal elements go away?
Well, off diagonal on what basis?
I see. I want to say the local energy basis, but that's the
But what do you mean?
That's ill-defined.
Yeah.
Yeah. Okay.
Right.
But is it well defined if you have a weak system that?
Right, but we don't.
We don't.
We're talking about a strongly interacting system in every subsystem, right?
Yeah.
So those are, it's impossible for the coupling to be weak.
So here there's no separation of timescales like in terms of the type that Gil's mentioning, where you first locally equilibrate and then.
No, you can have that, yeah. No, I haven't really talked about timescales, right? You could have this be a system where, yes, it equilibrates quickly here, goes to local equilibrium, and then there's a longer time scale associated with transport across the whole system.
What do you mean in terms of the components of the
No, that was interesting stuff. Okay, so the slow stuff is near the diagonal, and the fast stuff is further off the diagonal. So if you ask about the matrix elements, which are just doing things locally around here, they're spread far away from the diagonal. They involve large energy differences. They relax fast. When you talk about the so the slowest operator is the energy density weighted positively here and negatively here, right? And that's going to measure the thermal transport across the whole system. That's going to be the slowest k-local, local type operator, right? And that guy will only have matrix elements very close to the diagonal because it has a very slow time. And in fact, we know it just decays exponentially, right? It's just relaxational. The amplitude just decays exponentially, so you can actually predict that the matrix elements will have an average distribution, which is Lorentzian, which is the Fourier transform of the exponential decay. So there's a lot of structure there. The matrix elements, as you go further, the matrix elements, as you go further and further away from the diagonal, correspond to different types of operators, which have different time scales. And each operator, is weighted. Some of them, the things which correspond to very slow things, they only have non-zero matrix elements really close to the diagonal. And if you have matrix elements very far from the diagonal, that's something which is going to relax really quickly. I'm assuming I've ordered these in order of energy, right? Lowest energy to highest energy or something, right? When I talk about distance from the diagonal, I mean this, energy differences. So I've got them in order by energy here. Yeah?
Something is not that clear to me. You're saying that the off-diagonal elements are going to add up decommunally.
At long times.
Yeah, but you haven't really done any time integration or, where is the summation? Where is the addition of the phases?
Right here. Right,
That's one of
so
the
this you plug into here, and this you plug into, here, and then you do this sum. So there's the sum over all the different terms. Trace over the bath. Because when you trace over the bath, you're adding up tons of different things.
Question?
Just a second, let me just turn the page. Yeah.
What do things like robust things like time reversal symmetry do here? Because then you will have these special pairs of states which are the same energy, and so their off-diagonal density matrix elements are also stationary.
Pairs of states of the same energy.
Right. So
what dictates pairs of states of the same energy?
Time reversal symmetry, for example, which will not be destroyed even if you mix it up very well. Oh, sorry. Time reversal symmetry and that's a spin-half system, which gives us Kramer's degeneracy.
Yeah.
So then you will have.
Then you'll have pairs of states.
Right.
So I guess what you do is on the diagonal, pairs of states that were degenerate, you would. Okay, so when we diagonalize it. Choose our basis.
Right.
Let's choose our basis so that any pair of degenerate states, or any set of degenerate states of the eigenspectrum of the Hamiltonian we'll choose the basis that diagonalizes the probability of the initial state. So in that little block, it's just diagonal, and everything off diagonal is 0. We can always do shift, just like you do in when you do perturbation theory, degenerate perturbation theory.
Okay. That makes sense.
Right. So we can definitely do that and make it so it's all zeros there, and so they're gone. And all those states, if ETH is true, they all are the same thermally. Right? You know, they might differ by a spin and a half, but you know, they're not going to differ extensively. Okay, and so this motivates another ensemble, which you may also hear about from Polyakov later. Okay, so this story here, so this motivates the so-called diagonal ensemble. Which is rho equals sum over n rho n of 0. So for a given initial state, we can just throw out all the off-diagonal terms in the probability operator because they're going to dephase and they're going to add up to something near 0, so let's just throw them out. Right? And this is what's called the diagonal ensemble, and that's one ensemble. And it depends on the initial state, you see. And let me just mention some other ensembles.
Is it for the entire system though?
Yeah, right. So here, everything on this board is about the full system. So this is an ensemble for the full system. And this ensemble, if I put it in here, this being equal to this is a triviality. Well, actually, no, it isn't a triviality. It includes this assumption here that the off-diagonal terms go to 0. Okay, so other ensembles are the canonical ensemble, so they're Boltzmann-Gibbs, e to the minus beta h minus mu n and other terms if you have other Lagrange multipliers. And then so this is Boltzmann-Gibbs, and then there's, say, GGE, generalized Gibbs ensemble, which is this guy with an infinite sequence of conserved densities. And this is what you have for integrable systems at late times. It goes to the GGE, and there's been a lot of work on that. And then there's, people can see down here? There's the microcanonical ensemble. Now, especially those of you who have taught statistical mechanics, the microcanonical ensemble has this annoying feature of you pick a window, and the window's kind of arbitrary. You know, it really bothers the teacher, and I think it bothers a fair number of the students. But here we get away from it because we take in the limit of one eigenstate. So when you do the microcanonical ensemble, you would say, oh, you know, let's not set this window in an ad hoc way. Let's use the system to pick its own window. But what scale to choose? There's really only one scale, which is the level spacing. Right? And so you just go down to one eigenstate. And if ETH is true, one eigenstate is a fine ensemble. It gives equilibrium. Right? So if the system thermalizes all these ensembles, well, actually, these aren't two different ensembles. These are just two cases. You know, this is the Boltzmann-Gibbs, where this is a finite thing in the sum, which is what you normally have, and then for integrable systems, you have an infinite sum. So these are really the same. So these three ensembles, as well as other ensembles you could invent that have the normal properties, they all are the same. If you put them in here, take the trace over the math, they give the same properties of the subsystem, right? And that's the standard thing you know from learning statistical mechanics. If you take an infinite system, you can use whichever ensemble is convenient. It'll give you the same answers as long as you don't ask the wrong questions, right? And it's only global questions about the whole system are different, but if you're asking about, you know, sort of subsystems or just one measurable quantity, they're all the same. Okay? And so here we sort of add to the thing there two things. I'm adding in the diagonal ensemble, which is a real favorite, as I said, of Polyakov. And I'm saying the microcanonical ensemble, we should take it to have an energy width so it only holds one eigenstate. And that's a good ensemble to use here for the purposes of looking at a subsystem and seeing the subsystem looks like a Boltzmann-Gibbs ensemble. Right, and when the system is localized, they're not all the same, because when it's localized, information about the initial condition that is in the subsystem stays in the subsystem. At least some of the information about the initial condition on the subsystem stays in the subsystem till infinite time, and so you don't go to equilibrium. The subsystem actually remembers some details about its initial state beyond these global things, right? And so that's what's going to happen when we have localization. This whole, all these assumptions are going to break down. All this whole story is going to break down. Okay.
Question.
Yeah.
So then in integral system, the conserved densities, the number of conserved densities scales with the size system, or the volume of the system.
That's right.
But in the, if many localization happens, then the conserved things will scale, the number of conserved things will scale as the number of the size of the Hilbert space, or scale with the still.
Well, you don't really have, when you have localization, okay, so you might have some conserved densities, but they don't get transported, so they don't equilibrate. You have other conserved quantities, which I'll talk about, but they're not densities. Right, okay, so when you're localized, the conserved densities don't get transported, and there are other conserved quantities, they also don't get transported, and so they stay. They can stay on the system till infinite time, and therefore. What is equilibration? Equilibration is really just forgetting the details of the initial condition. Equilibration is really a statement about information. Right? The information about the initial state is hidden in some sense. It's gone, spread around so that you can't see that information locally.
What's the difference between these ensembles? If your system thermalizes, I don't see where these are all identical. I mean,
No,
isn't
not for the full system. Okay, so these for the full system are different. Right? This guy's only got one eigenstate. This guy's only got one eigenstate populated. These guys have all eigenstates populated with a very particular function. And this guy has some eigenstates populated with whatever function you chose here.
with the initial state?
With the initial state. So here you can pick whatever you want. Here it's a particular function, Boltzmann-Gibbs. And here it's a delta function, Kronecker delta function. So they're all very different in terms of
Right, but
in terms of the full system.
But if the system thermalizes, that means by your first line there is that they all will give the same.
They'll all give the same properties if you only look at the subsystem.
Right.
Right. So thermalization is not thermalization of the detailed properties of the full system.
So when you talk about thermalization, you always refer to the subsystem, right?
Yeah, in order for thermalization to sort of have a well-defined meaning, I think you have to. Yeah. Okay, so now I'm ready to talk about this. Okay, so testing this is hard, okay? So testing ETH and this whole story is hard. Right? Because it's the statements about all the eigenstates of the Hamiltonian. We're talking about complicated Hamiltonians. And really, to properly test it, the only thing I'm aware of that does that seriously is exact diagonalization. Right? And you're talking about not something where you're looking at the ground states. You can't use Lanczos. You're doing a complete diagonalization. So you're just doing small systems, 20 spins or something. That's the scale where you can do this. And you don't want to just do one system, you want to do a bunch of them to test it, right? Because you want to get statistics and see, is this really true, right? So you don't want to, you got to do a small enough system so you can do a bunch of examples and get some statistics and right. So it's hard, right? But people have been doing it, and it seems to hold up for the type of systems it should, right? And these guys started that. They did Bose-Hubbard model, 20 sites, 5 particles, I think. Various non-equilibrium initial conditions. And I've done that. My student, R.G. Paul, did some studies, and Kyung-Won has done some. And a convenient test, which we invented, they did it differently. A convenient test is look at and okay, so diagonalize the Hamiltonian, list the states in order of energy, like I did here, in order of energy. Take 2 states that are adjacent in energy from the middle of the spectrum. The energy difference, En plus 1 minus En, will be of order 2 to the minus the number of spins, if we're talking about 2-level systems with n spins. So this goes to 0 exponentially as you take the thermodynamic limit. And then what you do is you just compare rho s in n and rho s in n plus 1. So you sort of skip the step of calculating this stuff, or this, calculating this guy. You just compare, right? If these guys are all equal to this, then we can just compare them to each other. If they're all equal to each other, things are probably fine, right? And we're looking, so a way to see the violation of the eigenstate thermalization hypothesis is you compare these. And you might just look at one spin, subsystem of one spin, or whatever size you want, but one spin is enough to see the violations. When ETH is true, this difference, the magnitude of this difference, rho Sn minus rho Sn plus 1, goes to 0 exponentially in n. And we saw that, Arjit saw that in the model I'm going to be telling you about later. And recently, Kyung-Won was looking at a model, non-integrable model, and instead of, so with Arjit, we just sort of did the average, and we didn't look for worst case, because of course, you want to ask, one of the statements is it's every eigenstate. Right? So you don't care about the average. Well, you care about the average, but you would want to know, are there outliers? Right? Because are there exceptions? And so he looked at this and looked for the worst case. And the worst case also was going to 0 as you took the thing larger. Even though the number of possibilities goes up exponentially, the worst case still was going to 0. And so it really seems to be true to the extent you can test it, which isn't much of an extent because of its exact diagonalization and we're talking about pretty small systems. Right? But we're talking about big Hilbert spaces, right? You know, you might say, oh, you just test it from, n goes from 8 to 16 spins. Or you could say you go from a Hilbert space from 500 states up to 60,000 states, right? 2 orders of magnitude, right? It sounds a little better. And the exponentials, it's converging exponentially, so things are, it looks reasonably good. But it's just numerical tests.
So in this case, you have the difference between the matrices. But that's not determined. That's for each individual entity of the matrix. So rho s, or because rho s is now the density matrix. So the probability.
Yeah.
So it's for each.
So yeah, the norm of the difference.
The norm. Okay.
Yeah. Now, did I answer the question about testing it? Somebody was asking me about testing it.
Yeah, I was wondering about these Poincare recurrences because you have to take the limit of time going to infinity. So
yeah. So the way we deal, okay, right. The way we deal with it, okay. So ETH is about the eigenstates, and there's no issue with Poincare recurrence. Now, what's going to happen here? Of course, you're going to have Poincare recurrences. But you have 2 to the n eigenstates with 2 to the n different eigenvalues. So they're going to become rare. Yeah, the time you're going to have to wait is going to go up enormously. And of course, if we take n to infinity first, right, and I don't think it happens, we didn't seriously look for Poincare recurrences in the things we do, but we got 65,000 eigenvalues. The Poincare recurrence, we could find a Poincare recurrence in principle, but it's probably, some incredibly challenging mathematical calculation to calculate the time, which is a 1,000-digit number when it happens, right? Way beyond the age of the universe. I think that's the situation. I haven't really thought it through carefully. But I think you basically avoid it by saying it's about the eigenstates, right? And the eigenstates, there's no time. The Poincare recurrences would be this statement here failing. The off-diagonal terms, so you'd say, the off-diagonal terms have these random phases and they're adding up destructively, and then the Poincare recurrence would be when, all of a sudden they all come back into phase and add up constructively and you're back out of equilibrium. And this happens, right? If you're in a system at equilibrium, it's always fluctuating out further and further away. It has a probability of any size fluctuation, right? And those really are baby Poincare recurrences, right? If you look at a system at equilibrium and you're looking for rare big fluctuations, what's happening is these phases off the diagonal here are just adding up in a way to make that particular quantity you're studying deviate way out in the tail of its Gaussian distribution, at that time, right? And that's happening. So those recurrences are the equilibrium fluctuations, right? And the tails of the equilibrium fluctuations are cases where the phases add up sort of better and better constructively to make a big fluctuation, right? And it happens, and it's physics. Yeah.
Sorry if you said this, but which quantities do you actually need to get in order to test ETH? You said you have to use exact diagonalization and...
Yeah, so we take the Hamiltonian, we exactly diagonalize it, we get the eigenstates in particular.
So it's the eigenstates.
We get the eigenstates, right? So we're diagonalizing it, we got to get the eigenstates, we got to deal with the eigenstates. We need to put the eigenvalues in order to know their energies, right? And then within each eigenstate, we need to do this trace and evaluate properties of the subsystem. But in practice, typically what you do is you just look at the expectation value of one spin. Because the probability operator for one spin contains 3 numbers, which are average value of sigma x, average value of sigma y, average value of sigma z. And usually there's a symmetry, so at least one of those is automatically 0 in every eigenstate. So in one case, in the work with Origin, we only had to evaluate 1 number, and with Hyung-Won, we had to evaluate 2 numbers just for the rho s of a single state.
Could you have gotten those quantities using Green's functions instead, or by first computing Green's functions?
Of what? Green's functions, you have a non-interacting system and you treat something perturbatively, right? I'm talking about a general strongly interacting system. There's no reference system here at all.
Okay.
Yeah. Okay.
So is it fair to say that the first line that you wrote on the blackboard is true also for classical system?
No,
But
no, it's false. Because if I start the classical system in a pure state, it stays in a pure state, and the subsystem, it remains in a pure state, and the equilibrium system is a mixed state. So it's false for certain initial conditions.
what is a pure state of a classical system?
A single point in the configuration space. Pure state means specify the state to the maximum ability you can in the theory, right? With minimum. So a single point in the configuration space. It has a deterministic orbit. It remains a pure state. You trace over the rest of the system. That's trivial. That just means cut it out. Look at the subsystem. In a classical system, trace over the. In a classical system, in a pure state, trace over the bath is trivial. It just means ignore the other degrees of freedom. Right? And the subsystem is in a pure state. So this is a stronger sense of thermalization than you have in classical systems. But it's basically, that's sort of a trivial statement, because as soon as you give the initial state of the classical system a little bit of uncertainty, it will thermalize. And of course, quantum mechanics insists you have such an uncertainty. So it's not really a profound statement, but it's an interesting one. Yeah.
So you're saying that you can tune the spin system of yours to when this quantity goes to 0, and then you can tune it to when it stays a constant?
Yeah, when it's localized. That's my next topic, is talk about localization.
Okay, so, I mean, how are you sure that as you increase your system size, it won't just start?
Well, we just see it's independent of size. You know, it's just absolutely flat,
But,
function of size.
I mean, how can you
And it's
say?
big. It's big and size independent. It's numerics.
But you
Right.
can't say for sure that is.
Yeah, it's numerics. Yeah, that, right. No, I don't want to sell that we've proved anything. Right? We've done numerics, and numerics can always mislead. Right? But I try never to oversell my numerics. Right? Unlike a lot of people who do numerics. And so what we see is it's big, the difference is big, and it's independent of the size. And from that, you can make the plausible extrapolation to infinity that it remains independent of the size to infinity. And we're assuming that that's true. But that's what you can do.
So at the same time, you could also tell us about the ensemble, right? Means when you are doing the diagonalization. Means what is this?
The ensemble is all the eigenstates.
Yeah, so you can tell.
So like in Jungmann's work, it was just one Hamiltonian, and the ensemble was all the eigenstates, which gets big as you take a big system. In Arjit's work, we had a random Hamiltonian, so we had an ensemble. I'm going to show his Hamiltonian. So there we had different Hamiltonians as well as, but you get an awful lot of data from just one Hamiltonian when you fully diagonalize it and work with all the eigenstates, which is something I realized right at the beginning with Vadim. You can see it's amazing what you can see in a 12-site system. If you fully diagonalize it and look at all the dynamics, it's just, one Hamiltonian. There's just an amazing amount of stuff there that is really well approximated for the small system. Right, if we've got 30,000 by 30,000, we've got 10 to the 9 matrix elements here. 10 to the 9 different frequencies. So if you look at the spectral function of the thing, it's got 10 to the 9 delta functions. And so you don't have to do I epsilon. You just bin them. and you get these beautiful smooth curves. It's amazing. For really small, amazingly small systems. Yeah.
Were you able to find out the form of rho s equilibrium, that it's canonical in some Hamiltonian that's related to the Hamiltonian of the subsystem?
We didn't really look at that.
Oh,
Right, he didn't look at that either. Yeah, I'm sure you could, but that wasn't really the interest. Shall I go on? One more.
Sorry, it's been bothering. Could you maybe clarify something about your expressions on the whiteboard? There should be a dependence in a finite system when you're testing both on the subsystem size and on the large system size, right? And that would be something that you should be able to test. So you test the 1 spin and 2 spins and 3 spins out of say 10.
Yeah, we didn't look.
Collapse onto one.
We didn't look into that. Yeah. Yeah, certainly. Yeah, if you make the subsystem of order the size of the system, you're going to start seeing big differences. Yeah.
Because what bothers me is that this is a much stronger statement than the 1 spin measured over the whole, right? You're saying that 1, 2, 3 should all go exponentially.
Right, but we're trying to test. We're trying to test where this is finite and this has gone to infinity. So I want the total system to be much bigger than the subsystem.
No, I understand.
And my total system is small.
And large n.
Yeah, right. Now there's a limitation of numerics. Yeah. Yeah. Now that would be interesting maybe to explore as you make the subsystem not so small. How does it all break down? But it hasn't been done that I know of. Yeah.
So are these matrices the same size? Rho S?
Yeah, it's the same subsystem. Same subsystem.
So you have the same subsystem. So then what's index n and n plus?
That's the label of the eigenstate. So 2 different eigenstates of the full system.
So then this rho is not a sum over all n's, but you pick particular elements of this sum.
So that's this guy here. Eigenstate n, trace over the path, probability of the subsystem. Right, so here I've taken 2 eigenstates adjacent in energy, calculated what's happening in the subsystem, and asked, how different is it? No? So we're in this ensemble here. Right? Single state. Okay, let me try to go to the topic, which is the reason I got invited to lecture at this school. So maybe I don't know, the organizers were getting impatient or not. Okay, localization. So my colleague Phil Anderson is going to turn 90 in December. And I'm 55. And he wrote this paper before I was born. Okay, so we're talking about localization, and of course it's Anderson localization. He still comes into work every day. Okay, so what are we now? So now H contains, well, you've heard about this, static randomness. Okay, so we're specifically talking about Hamiltonians which have some disorder in them. Okay. Now there's 3 versions of this. Okay, so there's what's now called many-body localization. Which is the thermodynamic temperature. Right, of course, in a localized state, it doesn't really thermalize, so there's not really a physical temperature. But at that energy density, you could do thermodynamics and define what ask what temperature would give you that energy. Right? So when I say the temperature, and I'm talking about localization, I don't mean there's a heat bath, there really is a physical temperature. I just mean at that energy density, what would the temperature be if I did thermodynamics, right? Well, we shouldn't do thermodynamics, remember, because the system doesn't equilibrate. But it's just a label. It's a proxy for the energy. It means energy minus the ground state energy proportional to the volume. Extensively excited above the ground state. And with interactions. Okay, so that's one. And this is what Anderson was doing, as I said. And then he made an approximation, which is non-interacting particles. Non-interacting particles in a random lattice or random potential, whatever. And that's also equivalent to linear waves, or phonons, or linear waves of various sorts in random media. So we could talk about localization of phonons or photons or sound or whatever you might want to be doing in terms of waves, and that's really the same as this. So there's classical wave localization, which has nothing to do with quantum mechanics. Okay? And so these both were in Anderson, famous paper in 1958. This is the problem he was working on. This was an approximation he made and made some progress on this problem. This one is most work, theory work, since then. I don't know what the ratio, since that time, the ratio of papers about this versus this, I don't know, it's probably, 25 to 1 or 100 to 1, something like that, right? Because this one, he wrote it in 58, nobody paid much attention, but then in the early 70s, Thales sort of explained what it was about. People said, oh, that's interesting, and it's been worked on very heavily since around 1970. With Thales. And then there is interacting and near t equals 0. These guys are isolated, so these guys are both isolated from the bath, from an environment. Near t equals 0 and coupled to some environment. And in particular, a big interest here is the transition from localized to non-localized as a quantum phase transition. So the metal insulator or the superconductor to insulator. Quantum phase transition. And this whole stuff here, this is most experimental work on the subject is really about this. So there's really sort of 3 different versions. This isn't low temperatures, right? This is general. This is about the ground state with the interactions, whereas this is with the interactions and the excitations. And this is what we're going to talk about today. This is minified localization today, tomorrow, and the day after. Experimental work in its matter. This one's being explored seriously in some cold atom experiments. In cold atoms, there's probably more experiments on this than there is on this. And hopefully they'll get to this. But so far, they're basically mostly doing that. A little bit of either this or this. It's not clear. Okay. so there's Anderson 1958, and then for this many-body localization, there's this paper which really brought the subject to our attention. Pascalina Altschuler, 2006, which I'll call EAA. I'm going to start approaching it the way they did, since I think for some of you who know localization, it might be most familiar. Not the way Anderson did. Anderson was looking at spins, and eventually I'm going to go back to spins. But Pascalina Altschuler, we're talking about particles hopping in a random potential. So they were sort of starting from here, what this became after everybody worked on it, and going back to here. You know, Anderson started here and went to this. And then this got a life of its own, and then BAA went from this back to this. And they sort of closed the circle, I guess. But it's a different perspective. Okay, so let's start with this. Non-interacting fermions. I'll do it in terms of fermions because it's more familiar and a little bit simpler, but it could just as well be hardcore bosons. Right. It's not that important. The statistics aren't important for what I'm going to be doing, but I'll just do it in terms of fermions because it's just more familiar. Okay. So we're going to have it. So now, type binding hopping model for fermions in a random lattice, n sites, I equals 1 to n. Some on-site energy. Ci dagger Ci. Spinless fermions, let's say. Or the spin label is a site label, whichever way you want to do it. And then hopping. So, short range hopping. Tij, Ci dagger, Cj plus emission conjugate. And all, just for convenience, it's not important, but just for convenience, let's say the hopping matrix elements are real. So we're in the orthogonal symmetry class. But again, that's not important for what I'm going to be saying, but it's nice to be specific. So we're concrete. Okay. Now, most of you have seen this before. We've got quenched random potentials, quenched random hoppings. They don't have to both be random. And you could have one random and the other not. But if there's sufficiently strong randomness, it'll be localized. The eigenstates of this the single particle eigenstates of this Hamiltonian will be localized. And so I just want to talk a little bit about sort of what you might call strong localization, sort of heuristically. Okay, so what do we have here? We have some site energies. So let's say here's Wi, and here's Wj. This is energy, single particle energy. And here's a tight binding orbital at this energy, a tight binding orbital at this energy. And this Hamiltonian has a hopping Tij, which hops it from here to here. Now, of course, there's many sites, but I'm just looking at two right now. Right? And if we diagonalize this, what you're going to get is strong hybridization between I and j. So the eigenstates of our system will be contain a lot of I and j if Tij is greater than or of order Wi minus Wj. So if the energy difference, if the hopping matrix element is comparable to or bigger than the energy difference, the eigenstates will mix these two things strongly. The eigenstates will be on both sides, so a substantial weight on both sides. And if it's the other way around, not if, this is trivial, but I'm going to reuse this in the many-body context, so I want to emphasize it. Not if Wi, Wj minus Wi is much greater than Tij. So this is what we call, what I would call strong localization, where the eigenfunctions of the Hamiltonian are, to a good approximation, just a single orbital with weak admixtures of the nearby orbitals that it goes to by hopping, but they're all off shell, and so they just mix in very weakly. So that's strong localization. And the states will be localized if you're in this regime, but then if you either turn down the disorder here or turn up the magnitudes of these guys, you can go into the regime where there's a lot of hybridization. And if there's a lot of hybridization pairwise, if this guy's hybridized with another guy and this guy's hybridized with another guy, you can get eigenstates which are extended through the whole system. So this can make extended states, extended eigenstates for dimensions d greater than or equal to 3. It turns out, for reasons that aren't important today, in 1 dimension and 2 dimensions, the weak localization effects, which are a little more subtle than this, mean that in 1 dimension or 2 dimensions, with disorder, all the single particle eigenstates are localized. But I'm going to stay away from that regime. I'm going to assume we're in the regime where everything's strongly localized. Yeah.
Sorry, how do you define short range hopping?
Short range in space. So we have a bunch of sites, perhaps on a lattice, perhaps not on a lattice. These hopping matrix elements, let's say they decay exponentially with the distance. So typically, physically, what happens is this is some tight binding orbital. It decays exponentially away from the site, and the hopping is due to overlap of those two orbitals, and so these Tijs decay exponentially with the distance. And so let's say that. Decay exponentially with the distance between the two sites. Or maybe it's on a lattice and we only have nearest neighbor hopping.
Okay.
That's a nice simple thing.
To enter the many-body localized space, do you have to, can this be in, say, another basis rather than real space, like localization in momentum space?
No. No. We need to think about the many-body Hilbert space. So right now we're just talking about the single particle Hilbert space. But we're not going to go to momentum space, because I'm assuming it's strongly disordered. Momentum is a lousy representation for this. So we're going to be in the strongly disordered regime where there's Hilbert space and real space. That's where we're going to be working, not in momentum space. Okay, so this is a single particle Hamiltonian. So the single particle eigenstates if they're localized, they look like this. Psi I goes as, say, some random function of I, and then they're going to decay exponentially away from position. Okay, let's say so let's say eigenstate n over c. So for the wave function will look like this at large distances. So eigenstate n will be localized near position r sub n, and the wave function will decay exponentially with the distance away from, with a localization length psi. And inside this exponential decay, there's going to be a lot of oscillations and randomness in some function here. Right? So this function isn't decaying strongly. I've got the decay and then the sort of randomness of the eigenfunction from all the scattering. This is going to look like this is going to look kind of random, this epsilon. Okay, so that's what the localized eigenstates look like at large distances, large compared to the localization length. These are single particle eigenstates, right? The extended states, psi I of n goes as constant, a noisy constant. So this is a constant that doesn't decay or grow with distance, but it's very noisy. It's positive and negative, so it's a funny kind of constant. It's like this function here. This is a constant that's very noisy. And so the state goes everywhere. And in fact, if you coarse grain in this regime, in some sense it thermalizes. Right? You start with a particle in this energy range in a wave packet, it'll just diffuse through the system and go to equilibrium, which is equally likely to be everywhere. Right? So this is like thermal. And it'll have diffusive dynamics. You make a wave packet, it'll diffuse, broaden diffusively. And then there's critical states in between. So this is only for d greater than or equal to 3. And again, also here, critical states where psi I. Okay. So there's a, so it's fi r to the minus 8. And in the critical regime, the wave functions decay with a power law, and inside of which, a power law envelope inside of which they're noisy. Okay. And there's a phase transition here, which is called the mobility edge, or the Anderson localization transition. And I want to introduce a term, and it only happens in d greater than or equal to 3 for the single particle problem with orthogonal ensemble. There's a symmetry class where you can get an Anderson localization transition in 2D, which Alex might mention, I don't know, but that's not relevant today. But I want to introduce a term here, which is when you go from this regime to this regime, it's a phase transition. The localization length goes to infinity. This constant goes to 0 as we approach it from this side. And you have to go to infinite distance to see that as a sharp distinction, so you need to take the thermodynamic limit. And so this transition from here to here is something that's an example of what we're calling an eigenstate phase transition, which is a phase transition that it's a sharp transition in the behavior of the eigenstates between two different regimes that are different in a sharp way, dynamically in this case, but it doesn't show up at all in the thermodynamics. Right? So when you do Anderson localization and you go through the mobility edge, say you change the energy from extended to localized, and go through the mobility edge, the density of states is perfectly analytic. There's not even an essential singularity that's been proved by the mathematical physicists. So an eigenstate phase transition is a phase transition that has absolutely no thermodynamic signature. So in that sense, it's not a thermodynamic phase transition, but it shows up in the eigenstates. When you look in the ensemble I was mentioning down wherever it was, the ensemble of one eigenstate, microcanonical ensemble of one eigenstate, and look at the property of that one eigenstate, you can see these phase transitions.
The property of that one eigenstate?
Well, like in this case, how does it decay? Right? What kind of fun, this is something goes everywhere, it's ergodic. This is something which is localized. Sharp distinction. If the system is inferior. Could be a symmetry breaking phase transition, and Raoul's poster, if you go to Raoul's poster tonight, he'll show you some other examples. But this is a single particle eigenstate phase transition, and I think it's the first example of an eigenstate phase transition to be in the literature. Although we just introduced the terminology just recently. Yeah?
I don't know if you plan to talk about this, but I want to ask. Is there such a criteria for many-body localization?
Which criteria?
So basically, you distinguish between two states by looking at states. In one case,
it thermalizes. ETH is true.
No.
It does not thermalize. ETH is false.
It's not. Just
that's the distinction.
Let's say you.
And it's here, right? This guy does not thermalize.
No,
if I start the particle here, it doesn't go to equilibrium. It stays where you put it. Okay? And I'm going to use exactly the same criterion for many-body localization.
So I'm not talking about thermalization.
So I am.
So basically, I have a state, and
Yeah.
it's a many-body state.
Yeah.
How do I know that it's localized or not? So do I have such a criteria?
In terms of the wave function, yeah.
Yeah, I have a many-body wave
Yeah.
function as I have
Yeah.
here, and I can, let's say I have a finite
What
system.
you do is you look at a subsystem, you take a trace over the path, and you look at the probability operator on the subsystem. And you ask, is it thermal equilibrium or not?
So you are saying that localization?
No, I do that here too. Right here, I take a subsystem, and I look and see on all the subsystems, is the particle equally likely to be there? Right? And it isn't. It's near R sub n, and it's not far away. So I can do exactly what I'm going to do for the many-body here. Okay?
I don't understand, sorry.
This wave function has the property that it's inhomogeneous. It's very different from equilibrium at this energy. Right? And this one is a lot like equilibrium at this energy.
So this is a
So we have something exactly like this for many-body localization.
So that's your criteria for localization?
Well, that's a criterion. Right. There's many criteria for localization. There's many criteria, but this criterion is not particularly different from the way you talk about it with localization, thermalization. It's not the way it's usually discussed because people weren't thinking in those terms when they were thinking about the single particle problem. But it really is the same stuff. It's just a matter of putting those words onto this, which is familiar. Yeah?
So in that localized wave function, are there, as usual, subleading power laws prefactors that you know if it can smoothly go over to the
What, here?
critical one? No, in the localized.
Oh. At distances shorter than this localization length, the behavior looks like this.
Right.
And at distances short, there's also a localization length associated with the crossover from critically localized to extended. And so if you're just on the extended side of the phase transition, at short distance you will see this, and then it'll go to a plateau. So this is the behavior at short distances when you're between the two, anywhere near the phase transition. But you want to go to, if you go to at infinite distances, only at the phase transition is it asymptotically like this. It's not really a subleading term, it's two regimes, right? It's a question of power law crossing over to exponential on a log-log plot versus power law crossing over to flat. Right? So if this is log wave function, log distance. If you're on the localized side of the phase transition, it looks critical at short distances. It's a straight line, power law, and then it rolls off to exponential.
Well, that's why I was just saying that the localized.
And this is at the localization length. And similarly, there's a localization length on this side here. In the extended, it's power law rolling off to a constant.
But I was just trying to say that a simple function that does that has a prefactor 1/r to the eta, so then I can send off localization link to infinity and have it smoothly go to the critical.
Yeah, but that's not accurate. When you really do crossovers at critical points, that's not what the function looks like. That's sort of,
There's some other.
it's a heuristic. It's a heuristic, which is, yeah. Problem is, I did my PhD with Michael Fisher, so I just can't be casual about that stuff. What did he say?
It's roughly like that.
Yeah, it's roughly like that, I agree. Yes. See, I'm a son and you're a grandson, right? See, the second generation, it wears off. Right, you were a student of David Nelson's, right? Yeah. Yeah.
So are you making any assumption about the sign of the domain, or?
The sign?
Yes.
No, the sign really doesn't do much in...
I mean, no, my point is that you have all the domain positive or all the domain negative, or it could alternate. And if it changes,
It could be any of them. Could really be any of them. Could be any of them, yeah. Yeah. I don't think I've said anything, or I will say anything that would be sensitive to that issue. Okay. Should I stop? Anywhere? I think I'll stop there, because anywhere I stop, it's in the middle. So let's just do a few more questions, and then I'll continue next time. Yeah.
I guess what I meant to ask about flow space versus momentum space is if you have an anti-symmetrized problem in some other set of variables, say like a kick rotor, is a anti-symmetrization in momentum space.
Yeah.
And there's no reason why you have to be potentially unifying localized space from looking at real space, because just you would also do it in momentum space.
Well, see, for single particle that works nicely, and you get localized in momentum space, but I want to put on some interactions, right? And having interactions that are short range in momentum space is kind of, I guess it's not completely artificial, but